Hi, I'm Dr. David Dobson. Welcome to Conversations. Today, my guest is Shabnam Ahadzadeh, an electronic engineer and a PhD candidate in a joint program between the University of Antwerp and Hasselt University. Today, we will discuss her PhD research, which focuses on creating near infrared organic light emitting diodes. Shabnam, it's a pleasure to have you here.
Hello, and hello to your audience as well. Thank you so much for inviting me. And it's actually a grateful opportunity for me to be here in this conversation and also share my PhD with you. Thank you so much.
Shabnam, you completed your engineering degrees in Iran and then moved to Belgium for your PhD. What inspired you to make that big move and explore a new scientific environment?
So actually, it's a very good question. Basically, I did my bachelor in my own hometown, but for master, I moved to Tehran, which is the capital of
Mm,
Iran.
mm,
And it was actually the time that I realized how it is amazing to see people, let's say, with different mindset, different culture, and with different like educational system. It was very inspiring for me because it helped me to grow. I felt it. And then I was always, I wanted to stay in academia, and I had two way, like in front after my master, to stay in my country and do a PhD or leave to apply abroad. And I was just looking for different projects, and I saw the project that I'm working on it right now. It was very similar to the things that I was doing in my master, and it really inspired me a lot. So
mm,
I just decided to apply for the position, and I got it. And it was like very nice for me because I, like, let's say, got out of my comfort zone, and I like to challenge myself this way. I think it was one of the best decisions that I made because now I am kind of going to have a, like, I'm a joint PhD student. So anytime that I think about it, it actually excites me because I will have two degrees, one in physics and one in engineering. And who says no to that? I mean, so it's very nice. I'm very happy with the path that I took.
Wonderful, Shabnam. Your doctoral program is a joint effort combining physics at the University of Antwerp and industrial engineering at Hasselt University. Can you explain how the dual degree structure connects the fundamental why physics with the practical how engineering?
Exactly. So, as you mentioned, the title of my work as well is about near-infrared organic light-emitting diodes, but it
Mm,
has two parts. One is
mm,
about material, and
mm,
the other one is the device.
mm,
So, it's very important to understand the material itself, its
mm,
characteristics, and prepare the
mm,
material before making a device. For example, let's say we have a table, we have different material to make that table, but we
yeah.
need to know if, like, we want something, for example, heat resistant or so
Mm,
on.
mm,
So in Antwerp, I study the carbon nanotubes, which
mm,
is the material that I'm using
mm,
in my OLED, and
mm,
the behavior of them, their
mm,
characteristics.
mm,
And then when it's ready, I make the solution of that and I take it to Hasselt. And
mm,
there is the time that I make the device.
mm,
So the technology that you are going to make that
mm,
device is very important. How
mm,
do you make it? How do you put the different layers together is very
mm,
important.
mm,
That's the part that the engineering section comes in. It's actually, I really like it, that is interdisciplinary, because I really like to go toward the real impact, let's say, devices and applications. And it's kind of like physics helps me to understand the material, and with engineering I can turn it into a device, and together I can get some applications, for example, for medical treatment and safety and so on. So all together is a very nice combination to have them.
wonderful. Shabnam, you are passionate about research that has a real world impact. What main problem do you hope your research will help solve for society?
So I would say I would like to make some medical devices at the end of the very end, to that is very affordable and accessible for everyone. Why? Because the device that I make can, it will basically give us near infrared light, The near-infrared light can be used for medical treatments, for example, to promote the wound healing. It's very important in the case of some kind of diseases, for example, diabetic people, because it takes very long time in for some of them that the wound heals, and it's very painful. So I think the day that but the devices, let's say, that we have now, either we don't have something similar, or they are like very expensive and they are huge. You have to go to clinics for that. But with the devices I can make, I think it will be more affordable and accessible for most of the people. And the day that I see that, like, some they have a little bit less pain with the device that I make, I think I reached my goal and my purpose that day.
Wonderful. Shabnam, your work is all about creating near infrared light, NIR. For listeners who only know what visible light, what is NIR light and what does it feel like to us?
So basically, near infrared light, or NIR, is
Mm,
just like right beyond the red light. So with visible light, we have,
mm,
let's say, yellow,
mm,
green, blue light.
mm,
We also have ultraviolet, for example, and so on, which we call them dangerous. And then we have near infrared light, just right beyond the red. It has longer wavelengths and it has smaller energy. But for example, ultraviolet would have like smaller wavelengths and more energy. That's the reason they are more, let's say, dangerous. Basically, we can just get the near infrared light from sun. It's the light that we cannot see it, but we can feel it as a gentle, warm heat.
mm,
And we have it from sun as well. I mean, so it's nothing that is very special.
mhm,
We have it everywhere around us,
mm,
but
mm.
we cannot see it.
Okay. The sun gives off NIR light. So why it is important for us to manufacture this light instead of just using the light from the sun?
Actually, it's a very good question, true. But the problem is, the light that we can get from sun, we cannot use
Mm,
it for medical application or
mm,
technical purposes because
mm,
it's not controlled.
mm,
We, for example, medical
mm,
treatment, we need a specific range of that NIR light with a
mm,
specific power and energy
mm,
that is not dangerous, and we can
mm,
control it and use it anytime that we want. Also,
mm,
like in Belgium, for example, the
mm.
weather is always cloudy. There is no sun anymore. Let's say so, like, really
I
not.
remember. Yeah, I don't think I remember any sunny days. I'm from Vancouver, so I'm used to the rain, so it's feel at home there. But you're right.
Yes, exactly. So it's very important to make some artificial near infrared to be able to use it for different applications whenever we want, in a, like, let's say, energy and in a wavelength that we want,
Mhm.
also in a safer way.
Yeah. Uh, the device are called NIR OLEDs, which is organic lights emitting diodes. Uh, we see visible OLED screens in our phones and TVs. Could you use a simple analogy to describe how an OLED sandwich turns electricity into light?
Yes, yeah, true. We have the OLEDs everywhere. I mean,
Mm,
the very simple one, which is not
mm,
organic, we have the light bulbs, let's
mm,
say.
mm,
They are just light emitting diodes. And then we
mm,
have OLED TV in our smartphone and so on, as you mentioned.
mm,
So, how they basically work, OLED consists of different material in different
mm,
layers. You can imagine like a sandwich, for example, which has different layers on top of each other.
mm,
So, each of this layer has a role. Some
mm,
of them have more, let's say, we call it in scientific world electron. Some of them has more holes.
mm,
And when that electron and hole combine with each other, we get light.
mm,
In the case of, let's say, our sandwich or like a building with workers, imagine you have some spots that are available in some floors, and then we have workers who are going to get some spot. So when they see a chair and or desk that is available, they get excited, and they can give some energy with that excitement. In our case, that energy is in the form of the light. So basically, you give the electricity, you move the electron and holes to that middle layer, and then they recombine, they meet each other there, they recombine, and then they give us the light. But why do we have different colors? Because we can get red, I don't know, yellow, blue, and so on. It depends on the that middle layer that we are using, let's say, and the thickness of that middle layer. Let's say we have a tomato in middle of our sandwich, and how thick is that tomato will give
Mm,
us different lights, let's say, in
right.
the simple way.
Interesting. Thank you for explaining this in layman's term. Uh, uh, Shabnam, to make your unique invisible light, you chose a very specific material, carbon nanotubes. What makes tiny carbon tubes so much better than other materials for creating the deep infrared light needed for medical treatments?
Indeed.
Mm,
So we have some current strategies to
yeah.
get,
Mm,
other than carbon nanotubes, to
mm,
get the near infrared to make generate near infrared
mm,
light.
mm,
But some of them actually are based on rare material that we
mm,
don't want to use them. They are
mm,
based on toxic material and heavy metals,
mm,
and they all are in a way that we don't want to use them in general, or
mm,
they are not compatible with the human body, so we cannot really
mm,
use them for medical applications.
mm,
Also, some other strategies that are not really toxic, but they
mm,
only can cover, let's say, until 800 nanometer of the wavelengths,
mm,
which is like, let's say, if the near infrared range is from 750 to 2500 nanometer, then they only can go until 800 nanometer, which means
mm,
that our applications are very limited based on that light that we are getting from them. But with carbon nanotubes, they have very high photostability and
mm,
thermal stability. They're compatible with human body, and
mm,
we can easily change their wavelengths and tune it between
mm,
800 nanometer to 2000 nanometer, only by
mm,
changing their chirality. And the chirality is the way, like, you
mm,
imagine you have a sheet of the graphene or a paper, and you're going to roll it to make a tube from that.
mm,
The way that you roll that
mm,
paper and
mm,
the diameter of that tube will give
mm,
us different chirality,
mm,
which each of them can give us different properties, different light and color,
mm,
for example.
mm.
So based on this chirality that we can easily adjust, I mean, it's not that easy, but we can adjust it, we can get different emission. So that's something that we don't have it in the other strategies.
Shabnam, your research focuses on an infrared light range above 800 parallelity, um, which is very promising for medical treatment. How might your NIR OLEDs actually be used to help a patient in medical setting? For example, wound healing.
Yes, so specifically, I'm getting an emission around 980 nanometer,
Hmm.
and I'm not a doctor or a biologist to
Yeah.
really be able to answer this question in
Hmm.
detail.
Hmm.
But near-infrared light actually is very well known to promote the cell migration and
Hmm.
also to improve the blood flow. So
Hmm.
technically, when you have a wound, you can, if it
Hmm.
helps to cell for the cell migration, and
Hmm.
it can wrap up the wound
Hmm.
faster, and also it's very good for the pain release as well.
Shabnam, NIR OLEDs are described as being thin, flexible, and wearable. Do you envision a future where people wear these devices, perhaps like a patch or a sleeve, to help with pain or healing at home?
Yes, actually, because actually, currently in Belgium, we have some companies who
Mm,
integrate some devices in some patches for
mm,
the medical treatment. I mean, not the OLED, let's say,
mm, mm,
but some sensors or different things. So I
mm,
don't think that is actually very far future,
yeah.
because OLED is very flexible and
Mm,
light. We are talking about like
mm,
10 nanometer, 100
mm,
nanometer things. So,
mm,
and you can make it on a very flexible substrate.
mm,
So
mm,
I see actually that very easily
mm,
to integrate some OLEDs in the
mm,
patches, and
mm,
then easily people, or
mm,
they can just keep it around their wound. It's
mm.
accessible and affordable. They don't need to go to clinics. They can change it anytime they want, and it will be also very cheap. It will happen actually very soon, I would say.
Shabnam, just people understand what is your life in a lab? Like, how do you spend time in a lab? Because I'm assuming that you spend a lot of time in the lab.
So, so yes, that's a good question. I am in two labs, one in
Okay.
Antwerp and one in
Mm,
Hasselt. They both
mm,
are different worlds, let's say.
mm,
So in Antwerp, it's mostly a lot of characterizations and
okay.
making the solution.
Mm,
For example, we have a powder of the black carbon nanotube. I have
mm,
to disperse it in water to make it
mm,
like in solution,
mm,
and then I have to characterize a lot with some techniques like Raman, I don't know,
mm,
photoluminescence to get to see how are they
mm,
emitting, for
mm,
example, or if
mm,
they have defect or
mm,
impurities and so
mm,
on.
mm,
And then once that solution is ready, I'm
mm,
just taking it, going to the other university in the
mm,
lab, and we
mm,
have different deposition techniques
mm,
that we can make a film from that solution. So
mm,
then I'm studying what technique I have to use, how
mm,
do I have to use, how to
mm,
optimize it.
mm.
So technically, it's like from 8 a.m. to 7 p.m. standing, let's say, in
Wow.
the lab.
Yeah,
Yes.
it sounds like more like a chemical engineering to me as well. Like you also involve
Very
chemical.
interdisciplinary, actually. It's
Yeah.
very interdisciplinary. A lot of
Mm,
chemistry, a lot of physics,
mm,
not the electronic engineering that I
yeah.
studied,
Yeah.
but a lot of
Yeah.
engineering as well.
And what about your lab in Hasselt?
So it's based on it's a printing lab, let's say.
Okay.
So we try to make it, let's say, 3D printer,
Yeah.
inkjet printing, spray
Mm,
coating. We make the devices there.
mm, mm,
So we have different inks, different material, and we use them to make different devices like sensors, transistors, solar cells,
mm,
OLEDs, and so on.
mm,
So it's the engineering. We get the, let's say, material from
mm,
physicists and chemists,
mm,
and then we make the device based on
mm.
their material.
Outside of health and healing, what else might your invisible light be useful in our daily lives? Perhaps in sensors or security systems?
I mean, indeed, actually, we have a lot of applications for it. For
Mm,
example, night vision
mm,
cameras,
mm,
one of the like most common ones. It is used actually
mm,
in fingerprint and security applications,
mm,
and I don't know, food quality, to check the food quality, for example, the sensors that we have in our smartphone, they are all based on the near
mm,
infrared. Of
mm,
course, different material can be used for the different
mm,
applications as well. It's not necessarily has to be with carbon nanotube,
mm,
but a visible communication, so many applications that can be used for that.
mm. You mentioned that you need a single specific type of carbon nanotube for your device, and that is mixed with many other types. Uh, Shabnam, how do you manage to isolate or choose only one perfect tube you need for your light?
So that's the biggest challenge. One of the biggest challenges, let's say, not the biggest one. That's the part that makes me to stay in the lab very long. So as I mentioned, carbon nanotube is inherently it's not
Mm,
soluble in water.
mm,
So we need to use some dispersing
mm,
agents, like that we call
mm,
it surfactant. It's similar
mm,
to soap. I
mm,
mean, it's kind of soap.
mm,
And with this way, we make the solution of the carbon nanotube, which
mm,
will give us a black, dark solution. That one has a lot of qualities like metallic, semiconducting, everything is there. And then based on some of the, we have different, let's say, diameters for the carbon nanotubes.
mm,
Some of them
mm,
are smaller, some of them are
mm,
larger.
mm,
And this surfactant that we have, sometimes they like to go, a specific surfactant likes to choose the, let's say, wrap around the larger diameter. Some of them likes to wrap around the smaller diameter ones. So what we make a medium with competing surfactants, with changing the pH, with changing the temperature and so on. And then based on this, we can make like a competition between the surfactant and the specific carbon nanotube, and we can separate, but of course it takes a lot of time and effort for that.
Shabnam, instead of standard manufacturing, you use a technique called ultrasonic spray coating, which you compare to a super precise spray bottle. Why is this method better for making your thin films than other techniques?
Okay, sure. So we have actually, we are using that ultrasonic spray coating,
Mm,
which is a little bit more advanced than just a simple
mm,
spray coating. But
mm,
if you just only imagine the spray coating is spraying of your wall in the room. It can be like a very large, you can spray a very large area in a very short time,
Yeah.
and almost you have no waste as well, because I mean you put everything, all the color on the wall, so you have no waste. So with ultrasonic spray coating is a bit more advanced because it gives like fine mist of the droplets. So the thickness that we get finally in a thin
Mm,
film is
mm,
very uniform, and we can get like a thickness of, let's say, 10 nanometer, 100 nanometer.
mm,
Of course, with the normal spray coating, the thickness will be much
mm,
higher to get a
mm,
uniform
mm,
layer. But also the most important thing I would say with ultrasonic spray coating is very sustainable, and
mm,
the material waste and material consumption is very low. I would
mm,
say is 99% we are using all the material that we have,
mm,
and we can make very thin layers, good layers with that. It's scalable and it's roll to roll as well. So in industry, you can have we have some things that we call nozzle, that the solution is coming out from there. You can put 10 of this at the same time and spray over like a 1 meter area. So it's very good for large area devices, especially.
Shabnam, you spent a significant part of your PhD solving the problem of removing a material called surfactant to make
Yes.
your device work. Could you briefly describe why this soapy material was blocking the electricity and how you finally solved that challenge?
So, as I mentioned, we need to have the surfactant
Mm,
because we need to make the solution of the
mm,
carbon nanotubes, but unfortunately, they
mm,
are insulator.
mm,
So it means that they don't allow the charge carriers to
mm,
move. So
mm,
imagine you have a closed door
mm,
in the
mm,
building and the
mm,
workers cannot even move to go to
mm,
that spot, available spots that we talked about there. So it's blocking the transfer of the charge and the electricity, and so we don't have any electricity passing to carbon nanotube. So we need to remove them, but
mm,
initially we needed to have them for sure to be able to make the device, I mean. So what I did, I tried different solvents to try to remove that surfactant, at least partially, from the carbon nanotube, that we can have some empty spaces, let's say parts on the carbon nanotube, that we can have some transfer of the electricity, let's say.
mm,
And I tried different solvents, and I found out ethanol and methanol are the ones that are not really, let's say, damaging the carbon nanotube, because you also can damage them, and we don't want to do that because we don't want to change their properties. But also, the ethanol and methanol can remove the surfactant at least more than 50%, which is, I would say, good enough to have some charge transfer. Of course, it needs to be still more efficient, but I'm still working on it right now.
Shabnam, looking back at your journey from engineering studies in Iran to leading to an innovative and interdisciplinary PhD here in Belgium, what is the single most important piece of advice you would give to young students who is considering their career in science and engineering, like especially like specialized areas in material science?
So I would say, first of all, they should try to get out of their comfort zone, because doing only the same thing always, or not going into higher education because like it's more difficult or risky or that kind of thing, you should not be like that. If they see a little bit they are passionate about science, or they want to know, they're curious, they need to get out of their comfort zone, and they take the risk by moving to other countries, by moving to other universities and taking the challenges. And for sure, that's one thing, that piece of advice that always the other PhD students, when I was a first year student, they told me. I didn't believe that, but now I believe it by my heart, depths of my heart, that you should not give up. And we learn always from the mistakes and the failures. So it's always important to stay consistent, let's say, and continue. It will give the answer. You will get the response that you want, maybe in different ways, but yes, it's, I would say, two things. First of all, don't take the risk, and don't give up, let's say.
You're almost completing your PhD. What's next for you, Shabnam?
Actually, that's a very difficult question right now for me because I love to be in academia and do research. But I mean, I found out to do the research, I don't need to only be in academia. There
Mhm.
are companies and R&D and those kind of things that positions that I still can do the research that I like. But let's say it is less how do you say it I don't know how to say it, but it's more secure job, let's say.
Mhm.
Because when you do the position, you always have to go as a postdoc, you always have to be worried, okay, I have to go for next postdoc, then I have to get the like I'm giving you very honest answer right now actually. So I don't want to be in that situation, that to be worried about my future career always. So I think I will do the research stay because it's still because I really love doing the research and finding out about new things. I'm very curious. I want to really find out, okay, what next, what will happen. So I cannot do something that is there is no research there. But I think I will move a little bit more toward the industry by using
That's
all the knowledge of that I have from physics and engineering.
wonderful plan. Shabnam, thank you so much for sharing your interesting research with us today. We wish you all the best and completing your PhD.
Thank you so much. Thank you so much for the nice questions, and thank you so much for inviting me. I am really happy to join that conversation. Thank you so much for everything.
Thank you.